right, so next we'll have Kurt Zeilenga, who's, God, I've worked with him since 1998. He was the founder of the Open LDAP project and foundation. Currently he's advisor to the project, working at ISO-DE now, with Steve here, right? Kurt's also done a lot of work on the IETF, in the LDAP protocol specs. Right now he's on the SASL working group, as well as LDAP Directorate and the Security Directorate. Anything else? I'll let Kurt tell you.
So much for just working. Yeah, unfortunately, they're not all there. But oh, there we go. Maybe. Well, what we'll do. No, just go ahead and put my old slides up here. We'll go from them. You know where they are? So you're going to miss some pretty pictures that I actually... why is it this one? Well, we'll just go slideless. We can do that. So I'm here to talk about SCRAM. SCRAM is a better password authentication mechanism. It stands for the Salted Challenge Response Authentication Mechanism. And usually it just comes right up. Yeah, it's done that a couple of times. It could be resolution. Do you have a different driver? For no. Oh, there it goes. Oh, okay. So, SCRAM. It's a salted challenge response authentication mechanism. Designed to work with SASL, and it is the latest in a series of password authentication mechanisms, and each one has improved over time, and each improvement is really designed to mitigate what's considered the modern threats, the threats of the day, and the threats that we think are coming. So, to understand why it's better, I think it's kind of wise to actually think a little bit about where we've been with passwords authentication through LDAP, and why we actually had to upgrade at different times our mechanisms, understand those threats, and understand the evolution, so we actually understand why this next evolution is needed. So, at the beginning of time, we had simple bind DN password. No confidentiality protection. Never authenticated the server. You never cared about where you're actually sending it to. You just trusted the network. We stored the password in the clear, and we did a simple octet-wise comparison on the server. Well, it wasn't too long before that was found not to be good enough. So somewhere, we decided LDAP got put over SSL. Yeah, it just kind of happened. We used SSL to give us the data confidentiality protection. And it was also driven by the fact that we also wanted to protect the data after authentication. But what we didn't do is we never, in this time period when it was introduced, we actually never verified those certificates, never verified that the subject was right in the certificate. So we really just used this, oh yeah, it's encrypted, so there can be no eavesdroppers, but we never checked that we're actually talking to the server that we think we're talking to. Okay, that's what we did. SASL came along about 1997 out of Carnegie Mellon University. And it came out of the email space. Email at the time, they had multiple protocols. They were mostly doing a very clear text authentication at the time. But there was some challenge stuff as well. And they really needed to have a framework so they could reuse authentication mechanisms across those different email protocols. So SASL was invented to provide a framework so we could have mechanisms across multiple protocols. And the first two mechanisms that came out for passwords was plain, which has the exact same properties of our simple DN and plus password. It's just a username as opposed to a DN. And then we have SCRAM, which is just a very simple digesting approach. Yeah, so here's what plain is. And in LDAP, we don't use it because we do have simple bind. So it's rarely used in LDAP. And again, SCRAM really doesn't bias very much because we knew we had to protect the data anyways. So we're using TLS, and this just didn't give us much value. So this also never got really used in LDAP. But there was the desire to do something better back when V3 was being designed. LDAP V3 was being designed. And the IETF undertook an effort to design a mechanism of the day to try to mitigate certain threats and came up with this thing called Digest MD5. One of the key things it actually provides is mutual authentication, which means that not only can the server authenticate the user can authenticate the server inside the actual SASL authentication mechanism. But it's rarely actually done right. It did have a security layer, so it could actually provide integrity and confidentiality protection of the exchange after the authentication, but it was actually pretty broken and never had interoperability with it. It also provided a mechanism for storing hashed passwords that could be used with the mechanism. Unfortunately, it was a password equivalent. And what that means is even though it's hashed, the server can still reuse it, or an attacker could use it to actually authenticate. So it's no better than having the clear text password, really. And so that was actually, nobody ever used the storage format. Along came RFC 2307, which is probably a very standard experimental RFC. This actually introduced hash passwords to the directory service. And this, one of the reasons why this never got standardized is it actually violates some aspects of the protocol. In the sense that you're not supposed to, like Andrew was saying, the server is actually required to store what the client sent. And also, you're not allowed to change syntaxes of existing attributes and things like that. So, but anyways, this is what everybody uses to store hash passwords. When it was introduced, the common hash mechanisms were MD5, unsalted, and crypt, the original Unix crypt. Over time, we've got a lot of other mechanisms added. Eventually, we got around to actually updating LDAP specifications and saying, hey, we really should stop using this simple authentication that's in clear text. Everybody ought to be using Digest MD5. And we really encouraged people to use TLS. This was late 90s, I guess. That's what we tried to do. I don't know, we didn't get very much traction on this. We internet password modify. The idea here was you don't necessarily know from a client perspective where that password's stored, and maybe it's not even stored in user might actually have multiple entries, and you don't know where the password actually might be. You don't know how it's supposed to be hashed, all of these things. So this was the idea here was you just tell the server, I want to update this user's password, here's the new password. It takes care of all the complexity, hides it from the client. Originally was just open LDAP, but I think it's pretty broadly implemented these days. To solve the problem with user password, not because it was by the standards had to be clear text, we introduced an attribute called auth password. Never used. We undertook an effort to revise the specifications. This was primarily done to solve a lot of interoperability problems that we had in LDAP. A couple good things that came out of this was we actually standardized how to deal with international usernames and passwords. Okay, the requirement here is because the server in general is going to store things as that octet string, or they're going to store a hash of that octet string. The normalization of international passwords is actually supposed to be done on the client. And what's supposed to happen is you're supposed to prepare. You take whatever code page you're in. You have to convert it to Unicode. You have to apply some normalization to it. And then you have to put it into UTF-8, and that's what you actually send to the server as your new password. Turns out that that's still probably problematic, and if you use umlauts in your passwords, you can have availability problems. You're not going to be able to log in everywhere. So still today, your passwords better be ASCII. Sorry. And the other thing that we did is the mandatory implement. We realized Digest MD5 wasn't working out. And so we changed the mandatory to implement authentication mechanism to use start TLS, do all the certificate checks, do the subject check, and then do simple DN and password. Note that this is mandatory to implement. It's not mandatory to deploy. Okay? You don't have to support password authentication in your deployments. You can turn it off. And if you can, do. So here's the current situation. The current situation is simple bind with the end and password is ubiquitous. It is what everybody uses almost everywhere. We're doing really good on TLS certificate checks. Most clients are actually doing pretty good with implementing the checks properly, including the subject name checks, which are very important. So very good. Unfortunately, we got users. And users are horrible at getting this stuff right. So we have a huge problem, what I refer to as the click-through problem. We throw up a warning saying we have a problem with the certificate, and the user just clicks through, because it's all okay. It must be okay. You know, the server administrator, he must have updated his self-issued certificate. You know, we had a mail server, or just our mail server last week. Our certificate expired, and someone administrator issued a new certificate. And of course, we all just clicked through and said, yeah, sure, let's talk. We want our email, damn it. Did anybody send a fingerprint? No. You know, so we have huge problems in the current use of TLS, and it's everywhere. And even as security experts, click through the damn boxes, because dealing with fingerprints is a pain in the ass. Hash storage is also very common. The only time I see use of clear text passwords stored in a directory is because they want to use a strong authentication mechanism. And to support those strong authentication mechanisms, you often need to have the clear text password to support those mechanisms. So you kind of have this catch-22. You want a stronger authentication mechanisms, but to get that, we end up having to have weaker password storage. And so most people have actually sided with having stronger password storage. And unfortunately, they're using much better algorithms than they were using before. In particular, salted SHA-1 is probably the most common hash algorithm out there used today. Or some sort of Unix-compatible updated crypt3 mechanism. But, so what's the problem? What's the problem today? Users still send passwords to servers without authenticating the server in clear text. This is because they click through those buttons, right? Users have to trust their server that the server is not going to do something nasty once they know that password. They're not going to impersonate the server somewhere else. And one of the other gotchas is the server kind of has to trust the client did all these TLS checks that we know that the user's not going to do right, right? So we still have problems. So SCRAM is designed to address these problems. So much like Digest MD5, the passwords are not sent to the server. Derived values are sent. Those derived values are not reusable in any way. The server can't take those and use them to authenticate somewhere else. Or so we've solved that problem where we want to make sure the server can't impersonate us. We've provided mutual authentication in the mechanism. And instead of tying this to the name of the server, what we do is we tie it to the server's knowledge of your password, and not the password itself, but the key that it stores to be able to authenticate your password. Okay, so we're able to, you're able to mutually understand that both people have some knowledge of what the password is, and therefore you can trust that you're actually talking to the right server. When we store this, we meant to have an example here, but without the network, it was kind of problematic to get an example here of what the actual hash looks like. But you actually can hash this password. It's actually based on what's called an HMAC, which is a hashed message authentication code. Unlike just regular hashes like MD5, we know is really has been effectively rendered not effective cryptographically as a simple hash algorithm. HMACs have not been found to suffer from those flaws. So an HMAC, even an MD5 one, is much better than an MD5 hash by itself. SCRAM is based on SHA-1, and it's an HMAC, and that means it's going to be it's going to survive a lot longer than SHA-1 will. So we store this thing in the server. But the cool thing is that that server can't use it to impersonate that user anywhere. It's simple bind compatible, so if you do need to support simple bind, you can authenticate against that shared secret as well. You can't support any other mechanism though, so you can't do digest MD5 against that SHA-based hash. But we still got a problem, and the problem is I should probably back up here a little bit. SCRAM does not provide a security layer itself. So after authentication, there's no TLS yet. I mean, it provides its own security layer. So we're assuming that there's going to be TLS, right, to protect the data. But that TLS still we have the problem that the clients are clicking through, the users are clicking through the TLS security. So yeah, now we have this very secure authentication mechanism, but we're still subject to hijack attack after the fact. And so we need to do something to block that hijack attack. And hijack attacks are very common, and you could be suffering from one right now today, because if you have an access point's a great place to put a man in the middle. And it's a great place to spoof everybody's certificates when they're connecting to their home email servers. And boom, you're getting everybody's email. Very easy attacks. You see them all the time in airports, actually. I've seen so many rogue access points inside of airports, it's ridiculous. It is a very common problem. You have to protect against hijack attack. So what we need to do is just assure that there's not a man in the middle. But we don't want to rely on the TLS certificate stuff, because that's going to suffer from the click-through problem. So we have this thing called channel bindings. And channel bindings are a way to ensure that the SCRAM client and server endpoints are the same as the underlying TLS client and server endpoints. So you're binding one channel to the channel below, and you're doing that in a cryptographically sound way. And that ensures that we have end-to-end encryption consistent with the endpoints of the authentication that occurred at the SASL layer. This is really good stuff. I'm going to really show you kind of what happened. So this is what we started with. Nice big protocol stack. Then we added SASL. We added SSL first, and then we added SASL above. Yeah, we put relays in here all the time, right? People do. That's like a NAT box, right? And we do proxies. You know, you can do netcat proxies or SSLs, whatever proxies. You can do relays. Oh, here's a full LDAP, full-on proxy, right? So those are various things that happen all the time in the middle. This is the common man-in-the-middle attack, right? So we're going to take over the TCP and the TLS. We're going to let those layers pass through. We're going to rely on the user clicking through all the certificate warnings that are popping up. even if you're using a good mechanism like SCRAM or Digest MD5 without channel bindings, we let the authentication pass. After the authentication's over, we can listen to everything that's going on up above. So what channel binding does is it says, I'm going to bind those channels together. I'm going to prove that they're the same endpoints. So then if I have a man in the middle, what happens here, I wish I had a little pointer, but the server goes, oh, hold on, my endpoint here is not the same endpoint there. I got a problem. I stop immediately, drop the connection. So with channel binding, you detect that situation immediately and you kill it. You don't have to rely on the client doing the authentication. The server can detect it itself and protect itself. We no longer have to rely on the user to properly go through those certificate warning dialogues. So we can do, this is allowed. We can still go through NATs. And so we're fine and handy. So I encourage you guys, if you want to know the details, the math behind SCRAM, read the RFC. It's RFC 5802. I suggest you don't bother. SCRAM is coming. It's in SASL. It's going to come to other frameworks. Channel bindings are coming. This requires specialized support in OpenSSL and other security layers to provide the right information up from the TLS layer up into the SASL layer. It's all coming. It's pretty much ready to implement if you're using OpenSSL and SASL. You can implement this now. We have a nice little white paper on this, and I'll probably be putting another one. You can read my paper as well. But every client developer here should make a plan to implement this and implement it soon. The other thing I would also encourage you to do is don't automatically fall back to SASL plain or simple bind over TLS. If you support a fallback, you are going to open yourself right back up to all the security problems that you are trying to solve by doing SCRAM. Don't do fallback. Establish your profile. I'm going to talk to this server. Establish what mechanism you're going to use at the same time that you're establishing what the server name is and where I'm going to authenticate. Establish that. Remember it. And don't change it without the user really forcing you to change it. I mean, give him lots of really warning dialogues about it, and hopefully he won't click through them. Anyways, that's SCRAM. Do we have any questions?
One of your diagrams had a full stack relay in it. What happens if you have that? Because an LDAP proxy is quite a likely thing in some environments.
Yeah, so let's... So what you can do, one of the neat little things about SCRAM is if you have an LDAP proxy here, you can proxy the SCRAM authentication inside the relay. So the relay, in cooperation with its server that it's proxying for, can authenticate the user and establish those channel bindings itself. It has to be done with the cooperation of the server, but it is actually supported. So yeah, you can still do this, and you can do it in a way that's actually quite secure. Whether it actually gets implemented, we'll find out.
I'd like to extend Andrew's question to whether you thought about, it's very common to use web applications, for example, and so the idea could be the user authenticates himself against the back end, but through using a web browser, through a web service, and accessing the LDAP server. Is that also possible? Because you said it's possible to proxy it, you know.
Which, let's say instead of that being LDAP, that was HTTP, right?
Yes.
Okay. The main problem is that HTTP doesn't have support really for SASL mechanisms. So if you actually extended HTTP to have native support for SCRAM inside of the HTTP protocol, then yes, you could do the same sort of proxying. Or let's say there was a protocol that was SASL aware already, like an email protocol. So you could actually proxy your email server can use that secret that's in the server to authenticate its user if it has the cooperation of that server. So yeah, you could actually have like SMTP or over there in LDAP here, and you can proxy it so long as the relay is in cooperation with the server.
Okay, maybe one could not use HTTP directly in the sense of adding additional headers or something like the authenticate headers, but maybe a web application could send some JavaScript to the client, and the client does the SCRAM.
Yeah, as long as the authentication mechanism is SCRAM at some level, then it will work. It turns out SCRAM is not only a SASL mechanism; it's actually defined as a GSS mechanism, so you can actually use it even more broadly than just in SASL.
The problem today is a little bit that the APIs does not provide the possibility to break up the various authentication steps. So in LDAP APIs, you don't have the possibility to intercept.
Yeah, well, most likely you'd have to end up implementing it part of the authentication mechanism yourself, or there might be ways in Cyrus SASL to step it and then grab the intermediate data and actually use that in another protocol. There's probably ways of doing it. Yeah, but I mean, the key thing is this is a better mechanism. Make sure you implement it with channel bindings, okay? And don't fall back. So let's have some lunch, huh?